So I'd like to tell you a little bit about symmetry today. So I was the main thing that we're going to miss by not having the projector is I was going to start out with a very nice graphic by the artist Moritz Escher. I wonder how many of you have heard of Moritz Escher? So most of you have. Okay, so this particular graphic that I was going to show is called gravitation. I don't know why it's called gravitation, but I'll describe it to you. So there is sort of a star-like figure that's all sort of white and pure and like carved out of beautiful white marble or something, very geometrical. And it has 12 points, and each point is hollowed out so that it makes a little house. So you've got sort of a 5-sided teepee, and then the doors and windows are carved in, are cut into the sides of this little 5-sided teepee, and there's a little dragon living in the house. And so four of its legs stick out 4 of the doors, and its head sticks out 1 of the doors. And so actually it's built on this thing, which is called the dodecahedron. How many of you know the dodecahedron? Okay, and why is it called dodecahedron? Yeah? It means 10 plus 2, and it has 12 sides, exactly. So this is the dodecahedron, and its faces are these pentagons, and in the figure graphic I was going to show you, there were little 5-sided teepees built up on each one of the faces, and these little dragons are living inside. And now you can see that this dodecahedron is a very symmetrical figure. It's got 12 faces, but I can move it so any one of the faces is up at the top, and I can rotate those faces 5 times, and I can also reflect that face. So I can take a plane, like if I hold it like this, I can take this vertical plane that's sticking straight out at you, and slicing down the middle of the dodecahedron, and if I reflected it across that plane, it would stay the same. So it has 12 faces, and any face can be on top, and then if I keep that face on top, there are 5 rotations, and there are 5 reflections, making 10 symmetries of the top face. So altogether there are 10 times 12, or 120 symmetries of this solid figure, the regular dodecahedron. So this figure of Moritz Escher has these little teepees on top with the dragons inside. And the dragons, of course, only have 1 head. They have 4 legs and 1 head. So he has broken the rotational symmetry of the top. You can't rotate anymore. The dragon will be facing in a different direction. So the question is there any symmetry at all of this picture, of this construction that Escher has made? And actually there isn't, because all the dragons are different colors, so that if you rotate it or try to rotate it, you'll ruin the colors of the dragons. But if you ignore the colors, then they are symmetrical in a certain way, and you can take any dragon to any other dragon. And that's sort of what I would like to explain, how that works. Okay, so this is the talk is based around the regular solids. So we were talking about the dodecahedron, but let me go through them. Probably, how many people know all the regular solids? A lot, but maybe not completely everybody. So let me go through them. So this is called the tetrahedron. It's a triangular pyramid. It has 4 triangular faces. They're equilateral triangles. And if I can put any triangle on the bottom, and then I can rotate it a threefold way, and I can reflect it through planes that that contain one edge and go through the middle of the opposite edge. Okay, so it has 4 faces, and each face has 6 symmetries, 3 rotations, and 3 reflections. So that's 6 times 4. This has 24 symmetries. And the next one is the cube, which everybody has seen many, many times, of course. And the cube has 6 faces, which are squares. And again, any face can be taken to any face. And then if you fix a given face, then again you have 4 rotations and 4 reflections. So that's 8 symmetries of the square, and then times 6 faces is 48 symmetries of the cube. And then there's the octahedron here, which has 8 faces. Again, the faces are now triangles again, and they're all equilateral triangles. And again, if I put one face on the top or the bottom, I can put any one of the faces on the top or the bottom. So that's 8 faces, and then it's a triangle. So as we said, there's 6 symmetries of the triangle. So that's 8 faces times 6 symmetries, altogether 48 symmetries again of the octahedron. So the octahedron and the cube both have 48 symmetries, and we'll see in a minute there's a very good reason for that. And then we come to the dodecahedron. So it has 12 faces, which are pentagons, and I've gone through the reasoning about that already. So it has 12 times 10, 120 symmetries. So quite a bit more than those guys. And then finally we come to the icosahedron, which is probably the most obscure name of all of them. So icosa happens to mean 20 in Greek, and it has 20 triangular faces, and so 20 faces and then 6 symmetries of the triangle make 120. So again, the icosahedron has 120 symmetries, the same as the dodecahedron. Okay, so I would like to spend a little bit more little time telling you about, in more detail, about the symmetries of the tetrahedron. And I guess the main point I would like to make is that these symmetries come in 2 types, okay? So when I was talking about them, I talked about rotations and I talked about reflections. And so rotations we can actually do. I can take this this tetrahedron and I can rotate it 120 degrees around the bottom vertex here to bring the top face back into itself. And I can do that. I can do that as many times as I want. I can do that around other vertices also. So I can do these rotations, and then, but the reflections I can't actually do, right? That you can imagine, it's easy to imagine reflecting in this plane. You can see that it could be done, but you can only see that. I can't actually do it, because reflections have kind of a drastic effect on everything. In particular, they change, it's a subtle thing, but it's pretty important. They change orientation, right? They would change, if I reflected myself, it would change my right hand into my left hand, and vice versa. And although we look pretty symmetrical, actually we're not quite symmetrical inside, and so my insides would get kind of mixed up if I were to reflect myself. And at a subtler level, actually, you would really be different because all the molecules in your body secretly have a hand in this. They're left-handed or they're right-handed, and they're all built to fit together properly. And if you reflected yourself, they would all fit together with themselves, but they wouldn't fit together with the rest of the world. And well, this would have some good consequences, like bugs are also built to, they're built to glom onto your molecules with the handedness they have. So if you got reflected, you would be immune to all diseases. But that probably wouldn't be very comforting to you because you'd die pretty quickly because you also couldn't digest your food. Well, anyway, okay, so it's got, so the tetrahedron has these 24 symmetries, and 12 of them are things that I can actually do. I can rotate. And let me describe for you, if I can, what those rotations are. So 6 of them are, well, so first of all, the most important one, and this is a really big discovery of mathematicians, is the most important one is doing nothing. Okay, this is called the identity. You leave everything alone. That will clearly leave the tetrahedron the same. The identity, you may have, I don't know if you've heard this word in your math classes, but has anybody heard of an identity in math classes? Yeah? Okay, so you're thinking in terms of doing things. Has anybody heard of 0 is the additive identity? How many of you heard of some statement like that? So that means that if you add 0 to any number, you won't change it, right? So 0 is called the additive identity because when you add it, it doesn't change anything. And the invention of 0 was actually one of the most important inventions of mathematics because it's what allows us to write our numbers the way they work and have everything work. So if I didn't have a 0, you would have trouble telling the difference between 31 and 301. There would be nothing to keep the 3 and the 1 apart. Right, so you would get confused about how big you wrote down the digits for the in the tens and the ones and the hundreds, and you didn't have a 0 to say there's no tens there. This 3 really means 100. You'd be in trouble. So the 0 is a very big deal, and in general, identities are a very big deal. And this was an important mathematical discovery. Anyway. Okay, so I can do nothing. That's one. And then I can rotate 120 degrees or 240 degrees around this vertex, or around this vertex, or around this vertex here, or around this one. So around each vertex, I can rotate by 1/3 or 2/3 of a turn. Okay, so that's 4 vertices and 2 rotations around each vertex. So that's 8 rotational symmetries. So I've got 1 for the identity and 8 for these rotations here. And then there's sort of a somewhat trickier set, which I take 2 opposite edges. So altogether the tetrahedron has 6 edges, right? There's 3 on the bottom and then 3 coming up to the top vertex. So it's got 6 edges, and they come in opposite pairs, like these 2 here, which are on opposite sides of the triangle. And I can drill a little, I can make a line between the middle of this edge and the middle of this edge, and then I can rotate by 180 degrees around that line. And I can do that with any of the 3 pairs of opposite edges. So that gives me 3 180-degree rotations. Okay, so that's 1 identity and 8 3-fold rotations and 3 2-fold rotations, altogether 12 rotations. And then just as we said for the face of the cube, right, it has, the tetrahedron, it has 3 rotations and 3 reflections. The other 12 of the symmetries of the tetrahedron are they're these orientation reversing kinds of symmetries that turn left hands into right hands. So again, several of them, I mean, there's one for each edge. For each edge we can take a plane there and going through the middle of the opposite side and reflect across the plane. So that's 6 reflections across planes. And then there's a trickier one. So it works like this. Again, it's going to break on me before I can finish. So you have to imagine what I do is I place the tetrahedron like this. So I've got this edge over here and this edge over here. And if I were to bring those edges, just bring them into the middle, they would span a plane, which is cutting the tetrahedron exactly in half. And if I reflect that tetrahedron across that plane, this edge will come over here, and this edge will come over here. Well, they won't match, right? This edge will look like this, and this edge will look like that. So they won't match, but then I can rotate by 90 degrees also, and I can bring them back together. And I have a choice. I have a choice of rotating this way by 90 degrees or rotating this way by 90 degrees. So there's 2 possible ways of rotating. So there are 3 pairs of opposite edges and 2 this is called a rotatory reflection. Okay, a rotatory reflection. So I reflect and then I rotate in the plane that I reflected in, and then I can do that with plus 90 degrees or minus 90 degrees. So that gives me 6 rotatory reflections that preserve the tetrahedron. Okay, so that's 12 rotations and 12 orientation reversing symmetries of the tetrahedron. Okay. And if I look at the cube, I can do a similar kind of analysis. There's going to be 48, but I think that so in the talk I was going to hold off on this, but probably doing it this way, it's good to point out this early. There's a very beautiful relationship between the tetrahedron and the cube. You see, I can put the tetrahedron inside the cube. And so it sort of occupies every other vertex. You see the green tetrahedron inside the blue cube. So it's occupying these vertices and these vertices, sort of every other vertex like that. And you can see it here, maybe the tetrahedron isn't actually there, but in this cube I have the one set of vertices colored red and the other set of vertices colored blue. And so I can put the red vertices will span a tetrahedron inside the cube, and also the blue vertices will span a tetrahedron inside the cube. Okay, so I can put a tetrahedron inside the cube, and this is a really nice way of doing it. And it turns out you can check that that every symmetry of the tetrahedron actually comes from a symmetry of the cube. Anything I want to do to the tetrahedron, I can do something to the cube that that will do that thing to the tetrahedron. And maybe I'll show you the trickiest. So the trickiest of the symmetries was this one where I had to reflect across a mid-plane and then rotate by 90 degrees. But so just reflecting is not a symmetry of the tetrahedron, but it looks really simple in the cube, right? What I'm just doing is I'm just taking two opposite faces and cutting the cube in the middle and then reflecting across those two opposite faces. And that preserves the cube perfectly nicely, but it takes this tetrahedron to the other tetrahedron inside the cube. So, but then if I rotate by 90 degrees, I move it back to itself. So, so that's sort of the explanation of the complicated symmetries of the tetrahedron. They're composed of two pretty simple symmetries of the cube, neither of which fixes the tetrahedron, but the combined action does preserve the tetrahedron. Okay, and so an important symmetry that the cube has that the tetrahedron doesn't have is central symmetry. So the cube has this point in the middle that's sort of halfway from each face, a central point, and if I reflect in that point, that is, if I take that point there in the middle, and then any other point, I say, okay, I bring it down to this point, and then I go an equal distance on the other side. That's called central reflection. Then that will preserve the cube. But again, it doesn't preserve the tetrahedron. Right? It will take a vertex of the tetrahedron to the opposite vertex of the cube, which is not a vertex of the tetrahedron. So the central reflection of the cube doesn't preserve the tetrahedron. It takes it to the other tetrahedron. And it turns out, so we have 48 symmetries of the cube, and 24 of them will fix the tetrahedron, and 24 of them will take it to the other tetrahedron. And the 24 that take it to the other tetrahedron, every one of them can be gotten by taking first the symmetry of the original tetrahedron and then doing central reflection. So the 48 symmetries of the cube consist of the 24 symmetries of the tetrahedron, and then those same symmetries are multiplied or followed by this central reflection. And it actually doesn't matter if you do the central reflection first or afterwards, you get the same result. Okay, so those are the symmetries of the of the cube and the of the tetrahedron and the cube. And I won't go into a lot of detail, but you can analyze the symmetries of the other regular solids in kind of a similar way. And again, so there's 12 of the symmetries of the tetrahedron are rotations, which you can actually do, and 12 of them are these orientation reversing guys that you can't actually do, you just have to imagine. Okay, so I want to we've gone through a lot of facts about these regular solids, so I'd just like to write down a little table for you of the various facts so we can keep them in mind. So, okay, so here's the tetrahedron. Here's the cube. Here's the octahedron. Here's the dodecahedron. Here's the icosahedron. Okay, and so they have points, or they have points which I will call vertices. right? These are the corners. And then they have edges. And they have faces. Okay, so I'm making a table here. And then they have, I claim that equally important to their nature as all these physical characteristics are these things that you can do to them, the symmetries of them. So there's the symmetries. And we distinguished the symmetries that we could do from the symmetries that we couldn't do. So let me also write those down. So the rotations, the ones you can actually perform. Okay, so the tetrahedron has 4 vertices. The cube has 8, 4 on top and 4 on the bottom. The octahedron has 6. So it has 1 on the top and then a square in the middle and 1 on the bottom. The dodecahedron, well, you can count it later. It turns out it has, well, it's not so. So it has 5 on the top and 5 on the bottom and 10 in the middle. 20 vertices. And the icosahedron has 12. So the icosahedron, so it has, again, it has 1 on the top and then 5 around it, and then 1 on the bottom and 5 around it. So 12. Okay, and maybe I won't just, you can have fun checking these things out yourselves later. 12, 6. Okay, so for the symmetries, it's always the case that half of the symmetries are rotations and the other half are not. And there's a good mathematical reason for that, which some of you may learn someday. Okay, so here's this table of facts about the regular solids, the Platonic solids, and notice that there's, the numbers are not all unique, right? There's repetitions of various of the numbers, and especially the number 12 occurs in every column. And so you might be curious, is that an accident? Or is there some reason for that? And I want to convince you that all these numbers 12 are actually the same. Okay, so there's only 5 of them, not a dozen, but I want to show you that they're all the same. So the first thing to understand is, I guess, and this is, so this is unfortunate that there's some good slides I have of this, but let me try to make this point. So if I take the dodecahedron, and the icosahedron, then, well, you see how things work. So the dodecahedron has 20 vertices, 20 points, and the icosahedron has 20 faces, triangular faces. And they both have 30 edges, and then the dodecahedron has 12 faces, and the icosahedron has 12 vertices. And that, again, is not at all an accident. This is something called duality, and you can, if this was small enough, I could show you, you can actually fit the icosahedron inside the dodecahedron in a very nice way. Namely, if you take the center of each face of the dodecahedron and you connect them all together, you'll exactly get an icosahedron. So that you could fit the icosahedron inside the dodecahedron so that its vertices were just touching the faces of the dodecahedron. Or you could do it the other way around, right? So we have 20 vertices here and 20 faces here. So if this were smaller, I could fit it inside and take the centers of the faces of the icosahedron, and then if I connected them all together, I would get a dodecahedron. So these guys are we call them dual to each other because the vertices of one correspond to the faces of the other. And if I do that, then you would see that each edge matches up with an edge. So like if I put the top vertex of the icosahedron up here, then there are 5 edges going down from it to the 5 vertices around it, and up here there are 5 edges around this face, so those would just exactly match up. So the 30 edges of each of them would just get paired off with one another, and it would all fit together. Okay, so the icosahedron and the dodecahedron are what we call dual, and you can see that would mean that, so if I put the icosahedron inside the dodecahedron in that way, so made of its vertices are the centers of the faces, it should be clear that every symmetry of the dodecahedron will also take all the centers of the faces to themselves, and so would preserve the icosahedron. So that's why they have the same number of symmetries. Okay, and so this duality is a very beautiful thing, and it seems quite natural when you see it, when it's pointed out, or when you discover it for yourself. But actually, so the Greeks were the first people to study the Platonic solids systematically. That's why they're called the Platonic solids. Plato was a famous Greek philosopher. And they were first discovered actually by the school of the Pythagoras, which was in the 500s BC. And Plato lived in the 300s BC. So it was about 200 years. So all the regular solids that have triangular faces, so the regular solids that have 3 things around a vertex, like the dodecahedron and the cube and the tetrahedron, they were all discovered by the Pythagoreans. And the other 2, the icosahedron and the octahedron, were only discovered by Plato's school about 200 years later. It took people 200 years to understand this this connection, that there were more. Okay, so and again, so similarly, the octahedron and the cube are dual, and maybe I can actually see, I can put the octahedron inside the cube, so its vertices exactly fit into the centers of the faces of the cube. And yeah, so the octahedron has 8 vertices, or 6 vertices, and the cube has 6 faces. The cube has 8 vertices, and the octahedron has 8 faces. And the 12 edges exactly match up. So again, the cube and the octahedron are dual to each other, and that's again why they have the same number of symmetries of each one. Okay, so with duality then, I have shown you that these two 12s are the same by duality, and these two 12s are the same by duality. Okay, so those 12s are the same. So what about, okay, so then we have to try to connect the cube or the octahedron with those guys over there, and then there's a 12 here, which seems quite different. It's not about physical things, but about actions, right? This is the 12 possible ways you can rotate the tetrahedron, and how can that be connected with physical things? Well, okay. So here we have, again, the tetrahedron inside the cube. And again, so if I rotate the tetrahedron, I'll also rotate the cube. So like I could rotate around this vertex here and do like that. And when I do that, of course, the edges of the cube move around just like everything else. And so if I single out one edge of the cube, maybe this one down here, well then I can, by rotating around this vertex, I can move it up here. And then by rotating again around that vertex, I can move it over here. So I can move it to any one of these things around this side. And then if I rotate around this one, I can transform those guys to things around this one. And so every edge connects up with one of the vertices of the tetrahedron, so that if I start with one edge and I do all the rotations of the cube, I will get all the edges of the cube. And so we say that the rotations act transitively, means you can get from any one to any other one. Okay? And so since there's the same number, right, there's the same number of rotations and cubes, that means that if I just pick one of the edges of the cube, then I can match the rotations with the edges. So I get a connection like that. Okay. So that one is connected with that one. So now my main job is to connect the cube and the octahedron with the dodecahedron. And okay, so this is, I think, where I wish I had my graphics. So again, if we start with the cube, okay, so here you take the cube and imagine that I had a plane that contained this edge of the cube. So it was resting on the cube along this line. Okay, imagine I had a plane there, right? Then the plane would separate space into two pieces, one below it and one above it. Okay, so, and the cube would be inside one of the halves. And now if I move that edge around by one of those rotations, I would get a plane along another edge of the cube. Okay, so since I can take that edge to any other edge, I can take that plane and rotate it around by the rotations of the tetrahedron and get 12 planes that are all resting on the edges of the cube. And and the cube is in one of the halves that the plane cuts space into. Now if I take those, if I intersect those, if I look at the things that are on all the right sides of all those cubes, I'll get some kind of a polyhedron that's surrounding the cube. Okay, so for example, if I have this plane over here and this plane over here, right? They're cutting off a little sort of a little house on top. Well, except we need also to cut off the edges. So a plane that's resting on the edge, this edge of the cube, is going to make some angle with the top face. It's going to make some angle with the vertical face over here. And those angles are going to, turns out, you can check, it's going to add up to 90 degrees. They're going to be a right angle. And one of them will be larger and one of them will be smaller. And if I rotate things around, turns out that the two, say I look at the ones with the larger angle, they're poking up like this and they're going to make a ridge in the middle, or sorry, with a smaller angle. And then so the two opposite ones will have the same smaller angle, and these two guys will have the same bigger angle. So they'll make a kind of a figure on top that looks what I like to call it a pup tent. Does everybody know what a pup tent is? So a pup tent is the thing that, so when the Army, right, used to go camping, I mean, living out in the field, they would bring these tents along that had two rectangular sides and a vertical ridge in the middle, I mean a horizontal ridge in the middle, and then two triangular faces. So that's a pup tent. And anyway, so that's what this figure will make along each above each face of the cube. And I should say, well, yeah. So I have some kind of a polyhedron. It has one face for every edge of the cube. So it has 12 faces, so it's a dodecahedron. But it's not a regular dodecahedron because this face can be in lots of different angles. If the angles are very, very shallow on top, it will almost look like the cube. And then as the angle varies, the pup tent's roof raises up. And when the pup tent is very, very shallow, the lines from these vertices coming in are quite short and the middle ridge is quite long. But as I raise it up, these lines from the vertices start getting longer and the ridge in the middle gets shorter. So at some point, they're going to be equal. And at that point, you get the regular dodecahedron. And I've got at least we can see a model of that. You can see here, I have this cube here in the middle. You see the bottom face here, the right face, or this face on this side, this face on this side, a face on top, back and front. So you can see I have a cube right in the middle of this dodecahedron. And one edge of the cube is going across each face of the dodecahedron. So you see on each face of the dodecahedron, you can see an edge of the cube going across it. Okay? So there we go. So they're really all the same 12. And it's fun to imagine. I'm really sorry I don't have this graphic. It's fun to imagine how the shape of these dodecahedra vary when you move the angle. And like I say, they start off looking almost like the cube, and then as the plane gets steeper and steeper, there's going to be a point. So so you raise it up to a certain amount, and then these lines here and this line at the ridge are all equal. As you continue tipping that plane, this is going to continue to shrink. And if you tip it to exactly 45 degrees, these two vertices will come together. And instead of having a 5-sided figure here, you'll only have 4 sides. And at that point, you get what's called the rhombic dodecahedron. So you have the rhombic dodecahedron, which is also a very symmetrical figure, but it's not considered one of the Platonic solids because the faces are not themselves regular polygons. They're not squares, they're bent, right? So they have all the same length edges, but the angles are not the same. So this is called the rhombic dodecahedron. And another way, here's another way of seeing the rhombic dodecahedron. It also, so it fits around a cube the same as the regular dodecahedron does. And you can see, if you look at how it fits around a cube, you see very clearly how it's made. So what you do is on each of the 6 faces of the cube, you build another cube. So I've got 6 faces on all 6 sides of the cube. And then you take the centers of those cubes and you attach them to the nearby face of the cube. And so the rhombic dodecahedron is made from the original cube, and then these little square pyramids built on each one of the faces of the cube. And so that's sort of the end point of the family. The family starts with being essentially the cube and ends up with being the rhombic dodecahedron. And in the middle, you have the regular dodecahedron. So that's what I wanted to tell you today. I didn't quite get to show you some of the nicer pictures, but anyway, I hope that that was of some interest. Thank you for listening.